problem again. Okay, so we're starting with an atom that has -6, -3, and -1 as its energy levels. Yeah. So the first thing we have to do is draw the energy level diagram. So we're going to draw 3 lines because we have 3 energy levels. So -6 is going to go on the bottom. Then we have -3, and then we have -1. Now, in addition to that, we also have to label the quantum numbers. So here we're going to have n equals 1, n equals 2, and n equals 3. Okay, so the next we have to find what the wavelength would be for each possible transition. So first we have to decide what are the possible transitions. Well, we could go all the way up to the top, we could go to there, and we could go to there. So for each of those, we have to find what the wavelength is. But first we have to decide what our equation is going to be to find the wavelength. So, because E equals Planck's constant times frequency, that's the equation we're going to be using, but we don't know what the frequency is. So, if we have V equals wavelength times frequency, solving for F, we're going to have frequency equals speed over wavelength. Now for the speed, because we're dealing, the speed is going to be the speed of light, which is c. So we're going to plug in c for v, and when we plug that whole thing in to here, we get E equals hc over wavelength. So now, solving for wavelength, we have wavelength equals hc over energy. Okay, so now we have to use that equation to find the wavelengths for each of those transitions. So first we're going to be going from n equals 1 to n equals 3. So from here to here, the total change in energy is going to be 5 electron volts. So if we plug 5 into the E for that equation, we will have wavelength equals hc over 5. And plugging that in, we will get that the wavelength equals 248 nanometers. Okay, our next transition is from N1 to N2. So N equals 1 to N equals 2. From there to there, the change in energy is 3 electron volts. So, plugging that in to this equation, we're going to get wavelength equals hc over 3, which is going to give us 413 micrometers. Or nanometers. Yeah, nanometers. Our last one is N2 to N3, so N equals 2 to N equals 3. From here to here, the change in energy is 2 electron volts. So change in energy equals 2 electron volts. Now we plug that into our equation. Wavelength equals hc over 2. And the wavelength is going to be, well, 620 nanometers. Okay. Now here, we have our atom is at the ground state, and it is going to collide with an electron, and the electron is moving at 1.3 times 10 to the 6th meters per second. So our question is, does the atom going to have enough energy to go from the N1 state to the N2 state? So, to get to that change in energy is going to be 3 electron volts. And so we have to decide if when they collide, is the electron going to bring enough energy to get to 3 electron volts? So because it's moving, we can use K equals 1/2 mv squared. So our m is going to be the mass of an electron, and the mass of an electron is 9.11 times 10 to the negative 31st. Our v is going to be what we have up there, so 1.3 times 10 to the 6th squared, and we multiply that out, we find that our K is 7.7 times 10 to the negative 19 joules. So, but this one is in joules, and this one is in electron volts. So, in order to compare the two, we have to change this to electron volts. And 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, which is on our table of information. So, if we divide this by 1.6 times 10 to the negative 19 joules, we are going to find that we have 4.8 electron volts. And because this is greater than this, which is what we needed, we're going to say that yes, the atom now has enough energy to go to the N2 state. Finally, we have part D. So now we're having our atom is decaying back to the ground state by emitting a photon. So first we have to calculate what the energy of the photon is in joules. So if it's going from this state to this state, it's going to be losing that much energy. So in our case, we're losing 3 electron volts. And we want to know what 3 electron volts is in joules. So as we set up here, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So if we multiply this by 1.6 times 10 to the negative 19 over 1 electron volt, we will get that we have 4.8 times 10 to the negative 19 joules. And then finally, we have to say what region in the electromagnetic spectrum is this radiation. So, in order to do this, we're going to look at what the wavelength is. So because we went from the N2 to the N1 state, in this problem we found what that wavelength was. So, that is 413 micrometers, or nanometers. So, radio waves are really big, and they go from they're like in centimeters and meters. X-rays are really small, so it's like 1.1 nanometers. But visible light goes from about 300 and something nanometers to 700 something nanometers. So because we have 413 nanometers, we are going to be in the visible light spectrum. And there we have our question.